Today we're going to cover a few important concepts in Chapter 7 which will be used in our study of logarithms in Chapter 8. So to begin with, let's talk about what is an exponential function. An exponential function is one where we have a base raised to a variable. And for the definition of an exponential function, our base has to be positive and it cannot equal 1. So these two are examples of exponential functions because you notice we have a base that is positive, and in neither case does the base equal 1. Let's take a look at what the graph of an exponential function looks like, and let's start with say -2, -1, 0, 1, 2, and 3, and we'll make a table of values here. If I put a -2 in for x, I get 2 to the -2, which is really the same thing as 1 over 2 squared, which is really 1/4. If I put -1 in for x, I get 1 over 2 to the power of 1, which is really 1/2. If I put a 0 in for x, 2 to the 0 is 1. If I put a 1 in, 2 to the first power is 2. If I put a 2 in, 2 squared is 4, 2 cubed is 8, and that'll be enough points to help me graph this function. So, first of all, we know that when x was 0, it was 1. When x was -1, it was 1/2. When x was -2, it was -1/4. When x was 1, it was 2. When x was 2, it was 4. When x was 3, it was 8. And so you can see we get a graph that goes up like this and that. So there would be the graph of y equals 2 to the x. Now, let's notice and look at the domain and range of this graph. The domain is all the real numbers because I can plug any value in for x and I will get a y value. My range, if I look at my graph, it appears that y is always above the x-axis, and so the range is y is greater than 0. Not greater than or equal to 0, just greater than 0. As far as x and y intercepts, there are no x-intercepts because the graph does not cross the x-axis. And for the y-intercept, we had one y-intercept at 0, 1. This function is increasing because if we look at it from left to right, it's going uphill, it's rising. And the equation of the horizontal asymptote, well, I do have a horizontal asymptote right here. So the equation of the x-axis is the line y equals 0. All right, let's take a look at an example where my base is 1/3. If we go through the same procedure, if I put a -2 in, and I'm going to work some of these out because they get a little trickier. If I get 1/3 to the -2, if you remember from Math 10, if I have a negative exponent, I can flip the base and the exponent becomes positive, so 3 squared is going to be 9. If x is -1, I'm going to have 1/3 to the -1, and if I flip the base, the exponent becomes positive, that's going to be 3. If x is 0, y is 1. If x is 1, y is 1/3. If x is 2, if I square the fraction, I square the top and I square the bottom and I get 1/9. So if I draw this graph at -3, it was +9. At, sorry, that was at -2, it was +9. Let me just fix that. At -1, it was +3. At 0, it was 1. At 1, it was 1/3. At 2, it was 1/9. So this time, I get a graph that goes down like this. And if I answer the following questions like I did for the last graph, okay, my domain, again, is x is all the reals. The range, y is greater than 0. As far as the x and y intercepts go, there are no x-intercepts again. I have a y-intercept at the point 0, 1 again. This graph is decreasing as it goes from left to right. And again, if I look at a horizontal asymptote, the x-axis, which is y equals 0, is the horizontal asymptote. And that is the information for that graph. So basically, you should be able to see the difference. If the base of my graph is bigger than 1, the graph is an increasing graph. And if the base of the graph is between 0 and 1, the graph is a decreasing graph. And those are the key concepts from section 7.1 and 7.2. One of the key skills we need in dealing with logarithms is being able to solve exponential functions. So in this section, we're going to look at solving exponential functions. An exponential equation is one that has a variable in the exponent. So this is an example of an exponential equation. And today we're going to learn how to solve exponential equations. To solve exponential equations, we often need to rewrite our equation so that the bases on both sides are the same. So we're going to practice, first of all, by rewriting each of these in base 2. Well, to do question A, I could rewrite 4 as 2 squared, and it's still raised to the power of 3. And using our laws of exponents, if I have double powers, I multiply them. So this is 2 to the 6. So 2 to the 6 is the same thing as 4 to the power of 3. 1 to the 8th, well, this is really equal to 1 over 2 to the power of 3. And if we move 2 to the power of 3 up to the top, it really becomes 2 to the negative 3. And 2 to the negative 3 is the same thing as 1/8. If I wanted to write this in base 2, there's a little bit of work involved here. First of all, I'm going to rewrite 8 as 2 cubed, and that's all to the 2/3. And if you recall from Math 10, the square root of 16 cubed is the same thing as 16 to the 3/2. The denominator of my exponent is the index on my radical. The numerator is the power on my radical. Cleaning this up, double exponents, I can multiply. 3 times 2 is 6, and 6 divided by 3 is going to be 2 squared. Here, 16 is 2 to the 4th, and it's still raised to the 3/2. So I have 2 squared times 4 times 3/2 is 12 over 2, which is 2 to the 6th. And now using my laws of exponents, if my bases are the same, I multiply, I leave the base the same, and I add the exponents, and 2 plus 6 is equal to 8. So 2 to the 8th is the same thing as the product of 8 to the 2/3 times the square root of 16 all cubed. Okay, now let's get into the actual solving of exponential equations. Exponential equations, when we solve them, we use this rule, which is called the equal powers and bases property of exponents. Basically, it says if I can get a single base of one side raised to a power and the same base on the other side raised to a power, if the bases are the same, then the exponents have to be equal. So let's take a look at this example here. I have 2 raised to the 4x equals 4 raised to the x plus 3. Well, we can clearly see I can get both bases in base 2. So the left side, I'm just going to leave as is. 4, I can rewrite as 2 squared, and it's still raised to the x plus 3. Now you have to be careful with this exponent here. So the left-hand side is not going to change. When I have double exponents, I multiply, and I have to distribute the 2 to both of these guys. So this is going to be 2 raised to the 2x plus 6. Now I have a single base 2 on this side and a single base 2 on that side, and if the bases are the same, the exponents have to equal. So therefore 4x has to equal 2x plus 6. And now I simply solve for x. I can subtract 2x over to get 6 and divide by 2, and x would be equal to 3. And that would be my solution. Okay, in this case, we can get both bases in base 3. So 9, I'm going to rewrite as 3 squared to the 4x, and 27 is 3 cubed to the x minus 1. Now, I'm going to clean up my powers, and I'm going to multiply my powers together. So on the left side, I'm going to get 3 to the 8x. Here again, I have to distribute. 3 times x is 3x. 3 times negative 1 is negative 3. Now I have a single base on each side, and they're the same, so therefore the exponents have to equal. I can subtract 3x to the left-hand side. I can divide by 5, and therefore x is going to be negative 3/5. In this case, it appears I have 32 and the square root of 2, so I can get these both in base 2. Now the square root of 2, if you recall from Math 10, is the same thing as 2 raised to the 1/2, and that's still all to the 6x. 32 is 2 to the 5th, all raised to the x minus 1. And now I'm going to clean up my exponents again by multiplying. 6x times 1/2 is going to be 3x. If I distribute the 5, I'll get 5x minus 5. And now I have a single base on each side, so the exponents have to equal. I can subtract 5x over, and I get negative 2x is negative 5. Divide by negative 2, and my x value is going to be 5 over 2. Now, in this question, we have 2x raised to the 7th. In this particular question, we have some issues because I can't get 7 in base 2. Okay, in Chapter 8, we'll learn how to solve this, but for now, we'll use technology to help us. So I know that 2 squared is equal to 4, and I know that 2 cubed is equal to 8, so 2 raised to some power between 2 and 3 has to equal 7. So we're just going to use our calculator and use a little guess and check here. If I go 2 raised to the 2.5, so 2 raised to the 2.5, that works out to be 5.65. Well, let's try something closer to 3. Let's go 2 raised to the 2.7. That equals 6.49. 2 raised to the 2.29 is 7.46, so it's a little bit bigger than 7. Let's try 2 raised to the 2.8. That works out to be 6.96, which is fairly close to 7, so I would say x is approximately 2.8. So again, we just use technology to help us with this problem. One of the applications of exponential equations are those dealing with compound interest. Now the formula for compound interest is a equals p times 1 plus I raised to the nth, where a is the amount of money at the end of the investment, p is the principal amount deposited, I is the interest rate, and n is the number of compounding periods. Now, another formula that's similar to this one is a equals p 1 plus I divided by n raised to the n times t, where t is equal to time, and the rest of the variables are the same as they are outlined above. I like using this formula better, and I'll show you as we work through the next example. It says John invests $5,000 into an account that pays 3.5% compounded quarterly. How much will his investment be worth after 7 years? So if we identify what we have, we know that the principal amount is $5,000. Our investment rate is 3.5%, and we always convert that to a decimal. That will be 0.035. The number of compounds, it says it's compounded quarterly, which means the interest is calculated 4 times a year, and the time that this is being allowed to grow is 7 years. and we are looking for the final amount. So my formula is going to be P1 plus I divided by N, all raised to the N times T. So my principal amount is 5,000, 1 plus 0.035 over 4, all to the 4 times 7. Now, when you're evaluating this, you need to work out this stuff in brackets first, raise it to that exponent, and then multiply it by 5,000. So, if I go 0.035 divided by 4, and add 1 to that, I get 5,000 times 1.00875. 4 times 7 is 28. So now I'm going to take this amount and raise it to the 28th power. And that works out, to be 1.27626. And if I times that by 5,000, it's going to work out to be $6,381.30. So your initial investment of $5,000 would grow to be $6,381.30 in 7 years if the investment paid 3.5% compounded quarterly. Okay, let's take a look at our next example. And this question is saying, determine how long $1,000 needs to be invested in an account that earns 8.3% compounded semi-annually before it increases in value to 1,490. So we're looking for how long, so we're looking for the time. So we know that my principal amount is 1,000. We know the final amount is 1,490. We know the interest rate is 0.083, and the number of compounds semi-annually means twice a year. So if we go to our formula, A equals P1 plus I over N, N to the T. I'll plug in my values. 1,490 is my final amount. 1,000 was my principal amount. 0.083, the number of compounds is 2, all over 2t. Now, when we're solving for t, again, we're going to have to approximate again using our calculator. And in Chapter 8, we'll use another technique. But my first thing I have to do is I need to divide the 1,000 over to the other side. So 1,490 divided by 1,000 is going to leave me with 1.490 is equal to, now I can work out the stuff in brackets, so 0.083 divided by 2 plus 1 is going to be 1.0415 raised to the 2t. So now we can do some guess and check to see how long we have to invest this in order to raise it to $1,490. So we're just going to do some guess and check here. If I put 1 in there, I'm going to get 1.0415. 2 times 1 is 2, so that whole thing's raised to the power of 2, and that's going to work out to be 1.084, so not quite equal to 1.49. So let's try t being 3. So this is going to end up being 2 times 3 is 6, 1.0415 raised to the 6th, and that works out to be 1.27. So let's try t being 5. 2 times 5 is 10, so 1.0415 raised to the 10th is 1.50, and that's fairly close. So therefore, we can approximate that t is going to be approximately 5 years. So we're going to have to invest for 5 years in order to raise that by $490. Okay, I hope that makes sense. There's your assignment today from page 364. If you have any questions, feel free to send me an email.